Additionally, including a physical scale in the background of the image allows the software to translate pixel-based distortion corrections into real-world measurements. This integration of physical scale ensures that the system can apply distortion corrections that are not only visually accurate but also correspond to tangible, measurable dimensions. The key to this system's effectiveness lies in treating each section of the image as a unique transformation. For example, one square on the checkerboard grid is treated as a separate unit, with its own set of data points representing the undistorted image. These data points are then processed to calculate the necessary corrections based on the observed distortions. The partial derivatives, computed from the Jacobian-like matrix, allow the system to adjust each section of the image independently, compensating for distortions caused by lens characteristics, lighting conditions, and even the user's environment. This method enables the system to handle complex, nonlinear distortions with high accuracy. The Jacobian-like approach ensures that the system can adapt to different lenses and imaging conditions, making it versatile and robust. Moreover, the simplicity of the Jacobian framework allows for real-time correction without requiring excessive computational resources. To further enhance the system's accuracy, we combine the Jacobian-like framework with parabolic overlays. The parabolic focal points in the overlays act as additional anchors, ensuring that the curvature of the distortion is accurately accounted for. This combination creates a multidimensional correction model that integrates both local transformations, from the dot matrix, and global adjustments, from the parabolic overlays. This layered approach further improves the system's ability to correct distortions with high fidelity, ensuring precise and reliable results. In summary, the calibration system built around the checkerboard grid, the Jacobian-like matrix algorithm, and parabolic overlays provides a comprehensive and adaptable solution for real-time distortion correction in imaging systems. By treating each section of the image as a unique transformation and leveraging both local and global correction techniques, the system is capable of handling a wide range of distortions and lens characteristics with remarkable accuracy and efficiency. The analogy of the dot matrix as a Jacobian-like framework emphasizes the mathematical rigor of the design by integrating geometric principles with real-world scaling, parabolic overlays, and parametric modeling. This method enables the system to achieve unparalleled precision in real-time body measurements and distortion correction. This layered approach not only ensures high accuracy but also demonstrates the potential of combining geometric principles with computational techniques in a user-centric design. The algorithm we are developing closely resembles the workings of a Jacobian matrix, especially when applied to geometric transformations, distortion correction, and body measurement systems. A Jacobian matrix represents the partial derivatives of a system's transformation function. In this case, these functions describe how dot positions, or even pixel positions, in a distorted image, input space, map to their true positions in a corrected image, output space. The input space refers to the distorted data captured from the user based on their pose, the backdrop, camera distortions, and lighting inconsistencies. The output space is where these distorted points are mapped to their true positions in a corrected image, which the system is pre-programmed to handle. Essentially, the algorithm computes a transformation matrix for every point in the image, mapping distorted pixel locations to their corrected counterparts. A transformation matrix is a tool in linear algebra that allows for the transformation of vectors or geometric objects from one space to another. Represented as a two-dimensional array of numbers, transformation matrices can handle various operations such as translations, rotations, scalings, shearing, and reflections. When you apply a transformation matrix to a vector, you multiply the matrix by the vector to achieve the transformed coordinates. This allows for operations like rotation, scaling, translation, shearing, and reflection. For example, rotation changes the orientation of an object, scaling stretches or compresses it, translation moves it to a different location, shearing distorts it along an axis, and reflection flips it across an axis or plane. In this system, reflection is particularly important, as it accounts for potential mirror image distortions, whether the user is taking a selfie with a front-facing camera or using a rear camera, for instance. This is crucial because flipping the image also introduces distortions, which need to be factored into the transformation process. Transformation matrices are generally square, e.g., 2 by 2 for 2D, 3x3 or 4x4 for 3D. They can also be combined through matrix multiplication to apply multiple transformations simultaneously. This allows the system to apply a combination of operations, from basic translations to complex warping, in one step. In our case, the algorithm creates local transformation matrices for each small region of the grid, where each region is defined by the arrangement of dots on the checkerboard. These regions, when tied to real-world coordinates via the physical scale of the checkerboard and the pixel coordinates from the camera image, enable the system to capture local distortions such as small-scale changes in position, spacing, and scaling, as well as global distortions like lens warping. The displacement of each dot from its ideal position provides data for calculating the partial derivatives, which measure how changes in one dimension, x coordinates, affect the other, y coordinates. These partial derivatives, together with the parabolic overlays, capture curvature-specific distortions such as barrel or pincushion effects. For each region, the system computes derivatives to describe pixel shifts in both the x and y directions. The Jacobian-like matrix, which models the distortion, is then assembled by combining these local matrices. The resulting global matrix captures the complete distortion model for the image. In turn, this matrix enables inverse mapping, which restores the original proportions and scale by mapping distorted pixel positions back to their corrected locations in real time. The power of a Jacobian matrix-like approach lies in its ability to capture detailed local distortions caused by variations in lens curvature, perspective, or pixel density. This method is versatile enough to handle a variety of camera types and distortion characteristics. It also processes images of varying resolutions by breaking them into manageable regions, such as local matrices, and combining them to create a comprehensive distortion correction model. If needed, the parabolic overlays further refine the correction by allowing the system to address distortion in smaller, localized areas. By zooming into a region defined by 4 neighboring dots, for instance, the system can make precise adjustments, improving the accuracy of the distortion correction even further. The interconnected nature of this system, where everything feeds into one another, creates a kind of fractal model, rooted in fundamental concepts like matrices, parametric modeling, squares, rectangles, dots, and circles. This ensures a coherent and scalable approach to managing distortions in a variety of settings. The final model, corrected using the global transformation matrix, allows the system to restore the image to its true proportions and scale. By anchoring the matrix to the physical scale of the backdrop, the system can handle missing or distorted dots through interpolation methods such as bilinear or bicubic interpolation. These methods ensure smooth reconstruction of the image, particularly for areas that are incomplete or contain distortion. The integration of parabolic overlays enhances the Jacobian-like algorithm by introducing curvature-specific adjustments, refining the correction for more complex distortion patterns. This is achieved by overlaying the dot matrix and checkerboard pattern onto the distorted image, extracting the positions of each dot, and calculating how much each dot has shifted from its original position. These shifts, described through partial derivatives, allow for the construction of a Jacobian-like matrix. Once these local matrices are assembled, they form a global transformation matrix, which provides the necessary adjustments to correct the distortion in the image. This matrix is then used to map the distorted dots back to their corrected positions, accurately restoring the proportions of the body. The system can also interpolate missing dots or body areas, offering precise approximations for arcs and distances, essential for dealing with curves rather than straight lines. This trigonometric approach helps with the overall accuracy of the system. Ultimately, the combination of the Jacobian-like matrix approach with parametric modeling and parabolic calibration leads to a highly adaptive and mathematically robust distortion correction system. This ensures that real-time measurements can be translated into accurate, real-world body measurements, which are essential for creating tailored clothing and enhancing the user experience. The system's flexibility and precision not only enable body scanning but also play a crucial role in product design, manufacturing, and the entire clothing production process. The approach is designed to be scalable, using robotics, sensors, and minimal human intervention to reduce labor costs and ensure a seamless, on-demand production system tailored to individual users.